Calculus isn't difficult. Don't make it. This is a line. This is another line. This line is a deep line. This is a shallow line. A line has an equation y equals mx plus c. The m is the gradient of the line. Now the gradient of the line is defined mathematically or in common terms as the rise over the run. This is the rise and this is the run. So gradient is the rise over the run. Mathematically speaking, gradient is change in y over change in x, or change in f of x over change in x. This is the defining principle of calculus. All of calculus came from this. I can decide to find the gradient of a line by drawing this triangle or using this triangle trick. I draw a triangle like this, and I can take from here as y1, and this is y2, x1, x2. So that I can find change in y and change in x. Technically, if I were to draw my triangle here, I will still get the same result. If I were to draw a triangle like this, the same results as if I were to draw a triangle like this. No matter how I draw my triangle, no matter where I draw my triangle, if it's on the same line, the gradient will always be the same. Every line has one gradient. The gradient determines how steep or shallow the line is. Let's look at the curve. Find the gradient of this curve. That was a trick question, you can't. Okay, fine, let's try the triangle thing. If I were to draw my triangle here, or a triangle here, triangle here, or a triangle here, realize that all these different triangles will give me different gradients for the curves. Realize that as my x value keeps changing, the gradient keeps changing. So in other words, we can say that the gradient is some function of x. The gradient is some function of x that we don't know. We can find this function of x to determine our gradient. Let's try the normal formula for gradient of a line. Change in x over change in y. So let's take a point here. Say p, x1, y1, and find the gradient of this point. Let's try using the formula. Change in y over change in x. So with the formula, we can say that change in y will be y1 minus y1 over change in x, x1 minus x1. This gives us 0 over 0. This is indeterminate. We can't do this, mathematically speaking, we can't do this. So what do we do? It means this doesn't work. Let's try something else. Let's try the triangle thing again. But this time around, we choose two different points. So let's see a point here and a point here. There's the point we're going to find the gradient. So P, right? And P is f of x, comma x. And this one is another point, say Pn, which will be f of x plus. It's over here. So there's a change in x between x and here. So this place is going to be x plus change in x. So f of x plus change in x, comma, x plus change in x. Don't get confused. What we are saying is that this point is a certain distance change in x away from the original point. So its function value is also a distance change in x away from the original function value. Alright, so we can draw a line from here to here, and then get our triangle and find the gradient of this. To get the gradient of this, we just use the formula. Gradient is equal to f of x plus change in x minus f of x all over x plus change in x minus x. This gives us m equals f of x plus change in x minus f of x all over change in x. Now, that's not what we want. We want the gradient at P, not the gradient between those two lines. So we get another point, say here, where n is a different number. So between here and here, so we can get the gradient. But we don't want the gradient between these 2 points. We want the gradient at P. So we just keep changing the point till the point is infinitesimally close to P, but not equal to P. Because if it's equal, it means change in x is 0. And if change in x becomes 0, we get something over 0, which is indeterminate. We don't want that in mass, right? So we get very close to x, but we don't get to x. We get very close to p, we don't get to p. We approach it without getting to it. So that change in x does not become 0. To do that, we introduce a new function called a limit function. So the gradient at the point p is the limit as change in x approaches 0, doesn't get to 0, approaches it, of f of x plus change in x minus f of x all over change in x And this is how you get the gradients of a curve. So this is the formula to find the gradients of any point on any curve. Alright, so let's try something. For example, if f of x, which is our curve, was x squared, to get the gradient at any point, or the gradient function at any point, we just use this, right? So it means that the gradient function at any point p is equal to f of x plus change in x, which will be limit as change in x approaches 0. F of x plus change in x is x plus change in x all squared. So f of x plus change in x. So it means wherever you see x, you put x plus change in x minus f of x, right? But our f of x is x squared. So we replace this with x squared all over change in x. So the gradient function at any point is the limit as the change in x is approaching 0 of this. This gives us x squared plus 2x change in x minus plus change in x squared minus x squared all over change in x. The gradient function is limit as change in x approaches 0 of this. See that this can take care of this. Now we're going to have 2x change in x plus change in x squared divided by change in x. So we are going to get the gradient function as the limit change in x approaches 0 of 2x plus change in x. This takes care of this and one of these. Right? So the gradient function as x approaches 0. We are not getting to 0, we are approaching 0, right? But here, to evaluate this, at this final point, we just say that if x, change in x is approaching 0, we assume it to be 0, even though it's not 0. But it means that 2x plus whatever tiny value that is approaching 0 will still be approximately 2x. So we say that the gradient function of any point p is 2x. So for a curve f of x equals x squared, the gradient function is 2x. This gradient function is what we call the derivative of the curve. The gradient function is what we call the derivative of the curve, written as dy over dx, or f prime of x. And this formula is called differentiating from first principles. You can use it to do almost any curve, not all, but almost any curve at all. You can use it to find the first differential or the derivative of the curve. You can find subsequent derivatives of any curve. For example, after getting this, you can still put this into the formula and get the gradient function of this gradient function, which will be the second derivative of this, or the first derivative of this. We'll get into that in subsequent videos, so don't concern yourself so much with that. Let's try differentiating from our first principle. So the formula is dy over dx equals limit as x approaches 0 of f of x plus change in x minus f of x all over our change in x. Alright, so our f of x is x cubed, so our f of x plus change in x will be x plus change in x cubed, which will be x cubed plus 3x squared change in x plus 3x change in x squared plus change in x cubed. Let's put this into the formula and solve. It means that dy over dx is limit as change in x. Change in x approaches 0 of x cubed plus 3x squared change in x plus 3x change in x squared plus change in x cubed minus f of x, which is x cubed all over change in x. This can take care of this. And we have all of these. This will take care of one of this, and one of this. So that we get dy over dx to be limit as change in x approaches 0 of 3x squared plus 3x change in x plus change in x squared. And if change in x is approaching 0, these two tend to 0. So we have dy over dx to 3x squared. Now notice, if you made a very good observation, you realize that when we differentiated x squared, we had 2x. When we differentiated x cubed, we had 3x squared. What is that telling us? We can see that when we differentiate a cubic function, we get a quadratic function, 3 to 2. When we differentiated a quadratic function, we had a linear function. Whenever you differentiate a function, its power grows by 1. You can keep that. You can even see that graphically. Choosing 3 points on the curve, realize that the gradient at this point, you can see that the rise to the run is decreasing. It's moving downwards. The curve is moving downwards. So if I were to draw a function of the gradient function, which is the derivative, I realize that this is coming down, so it's definitely somewhere in the negatives. Change in y is negative, it's coming down here, and x is going here. So it will be somewhere here. Realize that y is going down and x is going here. So the point will be somewhere here. If I was to take a gradient here, I realize that x and y are both 0. So it will be 0, and if I were to take it here, you realize that y is going up and x is also upward. So it will be somewhere here. You draw the graph, a linear curve appears, a linear line function appears. So from quadratic you get a linear function. From cubic you get a quadratic function. But it's more difficult to show that graphically. But yes, you will see it if you differentiate and you plot the graphs. It's very simple, very easy. Calculus isn't difficult. Don't make it. The next thing is the power rule. If f of x equals ax to the power n, then f prime of x is equal to a n multiplied x to the power n minus 1. This is known as the power rule. So let's use the power rule to solve these questions. From the power rule, dy dx is equal to a n x to the power n minus 1. If y is equal to ax to the power n, so our a is 2, our x is there, n is 3. So definitely a will be 2, n is 3, x to the power 3 minus 1. Then we get 6x squared. Second question, our a is 5, our n is 2, x 2 minus 1. This gives us 10x. So try the last question on your own and let us know the answer in the comment section. Differentiate 7. Find the first derivative of 7. How do you do that? It's actually quite simple. You can either use the power rule or you can differentiate from first principles. So from first principles, you realize that our y is 7, or f of x is 7, so that dy dx is equal to limits as change in x approaches 0 of f of x plus change in x minus f of x all over change in x. Y is 7, f of x is 7. F of x plus change in x. This means that whenever you see x, replace it with x plus change in x. Since there's no x in 7, you can't actually put it anywhere. So this will still give you 7. Alright, so dy dx becomes limit as change in x approaches 0 of 7 minus 7 divided by change in x. This gives us limit as change in x approaches 0 of 0, which is 0. So dy dx is 0. And it's not only for 7. You realize that if there's any constant here, you won't have an x there. So replacing 7 with a, the equation still holds. the idea still holds, and you get 0. So when you differentiate any constant at all, you get 0. You can also take it from the graph. When you draw a quadratic graph, the differential of a quadratic graph gives us a linear graph. When I differentiate a linear graph, I get a constant, which is like this. So when I differentiate a constant graph, what do I get? I get 0. Alright? So when you differentiate a constant, you get 0. Differentiate a quadratic curve, you get a linear curve. Differentiate a linear curve, you get a constant curve. Differentiate a constant curve, and you get 0. From our knowledge so far, how do we differentiate this? We just take them individually and solve them, and we put our answers together. So with the power, we differentiate this, then we differentiate this, and put our answers together. So when I differentiate 3x cubed with our power, it means 3 multiplying 3, x to the power 3 minus 1, minus 4 multiplying 2, multiplying x to the power 2 minus 1, plus 7 multiplying 1, x to the power 1 minus 1, plus differentiate the constant to get what? 0. It means that we are going to get 9x squared minus 8x plus 7. And that is our result. Again, proving that when you differentiate a cubic curve, you get a quadratic. With our knowledge so far, solve this and put your answers in the comment section. I believe you can do all of this simply with no problem at all. See you in the next video. Continue to discuss and break down the complexities of calculus to make it easy for you and for your understanding.